Hi, everyone. My name is Alexia Dubreuze, and my partners are Evana, Luis, and Sarah, and we'll be focusing our project on electrochemical reduction of CO2, and we're Group 10. So a quick breakdown of our project. It will be broken up into 4 sections: the problem, our approaches taken, the results, and the importance of our finding. So to start, again, I'm Alexia Dubreuze, and I'll be discussing the problem that we're addressing, as well as a quick summary of the whole project. So as previously stated, our project is on the electrochemical reduction of CO2 to formate. Now, as you can see, this is a multi-step reaction in which there's an exchange of electrons and protons. But the most important step to note is step 3. Here is where CO2 is actually reduced to form our desired product of formate. And this is also the step that will be modeled in the MATLAB, and you'll see in the future slides. And then as far as the reactor, we'll be doing our project in the microreactor. Now, this is a nice little breakdown of what a microreactor looks like, but this isn't exactly our project. But essentially, our CO2 will be entering that cathode, and it will be producing, again, our formate, our desired product. And a breakdown in our MATLAB will show how efficient this process actually is. An example shown here is very important, just to kind of understand what the breakdown is for our whole project. But as far as microreactors go, it's important to note that they're very safe and very equipped to handle electrochemical reactions due to their small inner volumes. And then as far as our industrial applications, so we will be producing around 20 tons of formate, or that's our goal to produce annually in our microreactor, and that will be discussed further in the future slides.
So now I'm going to discuss the approaches taken to achieve these 20 tons of formate. But before that, I'm going to discuss the considerations taken. Firstly, for CO2 and HCO minus, also known as formate, we refer it as A and B for the sake of abbreviation. For the productions rate, we take into account only 1 out of the 100 channels in the total reactor. And through that channel, there's only going to be 600 micromoles per second of CO2. We take into account the ambient pressures and temperatures, as shown there. The mole balance that was used was basically a function of flow rate with respect to volume, and that will be equal to the rate law for A and then for B. The literature that we obtained from these reactions did only provide the Gibbs free energy of activation instead of activation energy, which made us use the Irving equation instead of the Arrhenius equation that it's commonly used. Now for the approach, we use the ODE solver from MATLAB, and that we follow 3 simple steps. We first set up the variables with the constants and the variables that were established previously, such as temperature, pressure, and initial flow rate. Then we wrote the explicit equations such as the total mole flow rate, the concentration of CO2, rate constant, and rate loss. And finally, we set up the differential equations for CO2 and formate, from which then we can obtain conversions and then plot them versus volume. And this is basically the code in which you can see steps 1, 2, and 3 from the approach we took.
So the next few slides are going to show our results, which was the output to the MATLAB. So this first chart is the flow rate versus the space-time tau. And tau is actually the time it takes for the reactants to go across the reactor. And it's expressed in the equation, which is volume over volumetric flow. And this chart actually shows the CO2 flow decreasing with time through the reactor as formate increases with time through the reactor. And so for this graph, it shows our conversion versus volume, and the conversion is increasing as the volume increases, which was our desired outcome. And this last graph, it shows the conversion versus tau space-time. And again, the conversion is increasing as the space-time is increasing, which was expected to have the formate increasing with time through the reactor. And it's important to note that this output from the MATLAB code, it models the production of one channel through the microreactor, but the reactor actually has 100 channels. So in theory, this translates to an overall production of 85.15 tons per year of formate production. And so this demonstrates that our reaction model was very efficient and had a nearly perfect conversion rate.
So now we will explain the importance of our findings. So in conclusion, the goal of our experiment was to take something simple like a textbook example and elevate it into something feasible or something that could be seen in the chemical engineering industry. As could be seen before, we produced great results. We achieved high conversions throughout our reactor, and we met the production requirements we initially wanted to meet. In this project, we were also able to delve deeper into a topic that we had not touched upon, which was microreactors, and how a little reactor like that could produce such good findings. We also were able to synthesize a product, formate, which is important in many industries, including the livestock industry. And that livestock industry is important to everyone around the world, and therefore it is a feasible process. And finally, the most important topic is we have touched upon global warming because CO2 as it is a well-known greenhouse gas. And we have created a process that can reduce the amount or the concentration of CO2 in the environment. And therefore, it is a step forward to creating a greener and more productive future. Thank you for listening. This was our project.